Hi folks, welcome back to another video on Advanced Higher Physics past papers, and this time it's the turn of capacitors and inductors. So as usual, we're going to the Calder Glen High School Advanced Higher Physics web page. Then we're going to click on past papers, and then the first link you see there is Mr. Davies' interactive PDF of Advanced Higher Physics past papers by key area. And if you click on that, then an interactive PDF opens up and you just click on the question you want. And in this video then, we're going to have a look at circuits, and in particular capacitors and inductors. And the questions we're going to have a look at are 2017 question 13 and 14 and 2018 question 15. So we usually only do 2 questions per video, but to save me doing 2 different videos for this, I'm doing 3 questions on capacitors and inductors. And we're going to start off then with 2017 question 13. And as usual, make sure you have a go at the questions first and then come back when you're ready and we will show you how we have worked through them. So question 13. A student purchases a capacitor with a capacitance of 1.0 farads, and the capacitor, which has negligible resistance, is used to supply short bursts of energy to the audio system in a car when there is a high energy demand on the car battery. And there's a picture of one there. In fact, you can buy these out of Halfords. The instructions state that the capacitor must be fully charged from the 12 volt DC car battery through a 1 kilo ohm series resistor. And for part A, we've to show that the time constant for this charging circuit is 1.0 times 10 to the 3 seconds. Well, it's a show question, so we have to start off with a relationship to work out the time constant. And that relationship is tau equals RC. It's the value of the resistor times the value of the capacitor. And the resistance was 1 kilo ohm and the capacitance was 1 farad. You're not going to get much simpler than this then. So 1 times 10 to the 3 times 1 is just 1 times 10 to the 3 seconds. And you should remember that the time constant is the time taken for it to charge up to 63% of its full value. Okay, moving on. Part B. The student carries out an experiment to monitor the voltage across the capacitor while it's being charged. And we've to draw a circuit that would enable the student to carry out this experiment. Well, we want a series circuit here with a capacitor and a resistor in it, with a DC battery power supply. So take your time with this, make sure you use a ruler and make sure you get your symbols correct as well. And if we want to monitor the voltage across the capacitor while it's being charged, then you need a voltmeter across the capacitor as shown in the diagram. That's just one mark there. Let's have a look at the marking instructions then. For 13A, there's the time constant equal to RC. Although notice they're using a small letter T there. It used to be a small letter T for time constant, but they changed it in 2019. It's now a tau symbol, so watch out for that. And in part B, we're looking for a circuit diagram with a 12 volt DC supply, resistor and capacitor all in series, values not required, but a voltmeter connected across the capacitor for 1 mark. Okay, part 2, the student draws the graph shown in figure 13A, and we've to use information from the graph to show that the capacitor is 63% charged after 1 time constant. Remember, the time constant we've just worked out is 1,000 seconds, 1 times 10 to the 3 seconds. So if we zoom in on the graph there, at 1,000 seconds, then the capacitor is charged up to, well, it's about, well, each wee box is 0.4 volts, so it's 0.4 volts away from 8, so that's 7.6 volts. So when the time is equal to 1 time constant, that's 1,000 seconds, then the voltage is 7.6 volts. The maximum voltage was 12, and 7.6 divided by 12 times 100 gives us our 63%. Remember, it's a show question, so make sure your final answer is the same as what you were asked for. And then part B, use information from the graph to determine how many time constants are required for this capacitor to be considered fully charged. So when do we think the graph reaches 12 volts? I think it's about there. and if we draw a little dotted line down, then that's 5,000. So the capacitor can be considered to be fully charged at 5,000 seconds. That's equal to 5 time constants. Let's have a look at the MIs. So the voltage at 1 time constant was 7.6 volts, and then 7.6 out of 12 is your 63%. And then part 2, part B, how many time constants does it take before it's fully charged? Well, again, we're getting that from the graph, or you might already know this. That is about 5 time constants. And indeed they're accepting between 4.5 and 5. Right, moving on, question 13C. The car audio system is rated at 12 volts 20 watts. Use your knowledge of physics to comment on the suitability of the capacitor as the only energy source for the car audio system. Well, you should know by now, use your knowledge of physics questions are open-ended questions, and this is your opportunity to put down as much relevant physics as you can to try and answer this question here. There's no marking scheme for open-ended questions. You just get 3 marks if it's a good answer, 2 if it's reasonable, 1 if it's limited, and 0 if there's no physics at an appropriate level in your answer. So let's see what we can come up with here. We're being asked about the suitability of a capacitor as the only energy source for an audio system. Well, the voltage across a capacitor will drop as soon as it starts to discharge, and therefore the current that it can deliver will also drop, but we're assuming here that the car audio system has got a constant resistance, and that it obeys Ohm's law, V equals IR. And if the voltage and the current drop as soon as it starts to discharge, then the power will also drop, since P equals IV, and we could sketch graphs of both the voltage and the current decreasing as soon as the capacitor starts to discharge. So the capacitor on its own won't be suitable because it can't deliver a constant power. We could also work out how much energy is available to be stored on the capacitor. That would be a half CV squared. So that's a half times our 1 farad capacitor times 12 volts squared only gives you 72 joules. And how long would 72 joules last us if the power was 20 watts? Well, that would be 3.6 seconds. And bear in mind that is if the capacitor could deliver a constant power. It would only last 3.6 seconds. So really, the capacitor is only useful to support a constant DC supply, or in other words a battery, and all it can really do is provide short bursts of energy when required. Would that get me 3 marks for an open-ended question? I don't know. Remember, these questions are marked holistically, so it really depends on whether the marker thinks that that's limited or reasonable, or whether it's a good answer. But remember, put down as much as you can. I would leave open-ended questions until the very end of the paper, and then if you've got time left, you can just put down as much as you can that is relevant and at advanced higher level. Alright, moving on. We're sticking with the same question paper because question 14 is on capacitors and inductors as well. Oh, like this one. A student designs a loudspeaker circuit. A capacitor and an inductor are used in the circuit so that high frequency signals are passed to a small tweeter loudspeaker and low frequency signals are passed to a large woofer loudspeaker, and each loudspeaker has a resistance of 8 ohms, and the circuit diagram is shown in figure 14a. Now the circuit is designed to have a crossover frequency of 3 kHz. At frequencies above 3 kHz, there's a greater current in the tweeter, and at frequencies below 3 kHz, there is a greater current in the woofer. And for part A, we have to explain how the use of a capacitor and an inductor allows, firstly, high frequency signals to be passed to the tweeter, where there's a capacitor in series with the tweeter. And capacitors like high frequencies. Why is that? Well, capacitors have got a low reactance for high frequencies. In other words, more current and hence more power will be delivered. And you can see that from the reactance relationship from your relationship sheet. Xc equals 1 over 2 pi Fc, so at greater frequencies you've got a smaller reactance. In part 2, How does the inductor allow low frequencies to be passed to the woofer? Well, the inductor has a low reactance to low frequencies, hence more current and more power will be delivered at low frequencies. And again, you can see that from the relationship for inductive reactance, XL equals 2 pi FL. So when the frequency is lower, the reactance will be lower. Only one mark for that though. Wonder what the marking instructions say. Well, there they are. So it really only says that the capacitor has a low reactance for high frequencies. Everything else is in brackets there, so that's all you have to say. And for part 2, the inductor has a low reactance for low frequencies. Remember, it's just one mark there for each of them. Right, 14b, at the crossover frequency, both the reactance of the capacitor and the reactance of the inductor are equal to the resistance of each loudspeaker. And we have to calculate the inductance required to provide an inductive reactance of 8 ohms when the frequency of the signal is 3 kHz. That's quite wordy, but basically calculate the inductance L when the reactance X is 8 ohms and the frequency is 3 kHz. So let's put down a relationship for inductive reactance, that's XL equals 2 pi FL. So the reactance is 8 ohms, and that'll be 2 pi times the frequency, which is 3 times 10 to the 3 hertz, times L, and then we're just rearranging to find L. So L will be equal to 8 divided by 2 pi times 3 times 10 to the 3, and if you do that in the calculator, you'll get an answer of 4.2 times 10 to the minus 4 henries, or 42 millihenries. There's the marking instructions. That's a bog standard 3 marker there for relationship, substitution, and final answer with the correct units. Okay, 14c, in a box of components the student finds an inductor and decides to determine its inductance. The student constructs the circuit as shown in figure 14b, and the student obtains data from the experiment and presents the data on the graph shown in figure 14c. And that graph has got the equation of the line for the rate of change of current for the first 5 milliseconds. And the rate of change of current is 20 milliamps per millisecond, or 20 amps per second. And then we've to determine the inductance of the inductor. So that's L we've to find, and we know di by dt from the graph. So the relationship we're looking for here is E equals minus L di by dt, where E is the back EMF produced across the inductor, and the size of that EMF is equal and opposite to the supply voltage when the circuit is initially turned on, and that supply voltage is 9 volts, so the back EMF at the instant when it's turned on will be minus 9 volts. So we can substitute that in, so minus 9 will be equal to minus L times 20, which was the gradient of the graph when it was turned on. That's the rate of change of current, di by dt. So now that we've got all them subbed in, let's rearrange it. The negative signs cancel out, and L will be equal to 9 divided by 20, which gives us an answer of 0.45 henries. And then for part 2, the student was advised to include a diode in the circuit to prevent damage to the laptop when the switch was opened. Explain why this is necessary. Well, when the switch is opened, the magnetic field around the inductor will collapse, so a large back EMF is produced when the switch is open, and the diode path in the circuit provides a means for the energy stored in the inductor to be dissipated as the magnetic field around it collapses. Only one mark there. Let's have a look at the marking instructions. So see part 1, there's a rate of change of current from the graph was equal to 20, and then substituting that into the relationship with the back EMF at the instant the circuit was switched on gives us our inductance of 0.45 henries. And for part 2, all they're looking for is that there's a large back EMF produced, but an answer explaining that a high voltage is induced or a large amount of energy is released from the inductor when the switch is opened is also acceptable. So that was two questions from the 2017 paper. Let's also have a look at a question from the 2018 paper. This is question 15. A defibrillator is a device that gives an electric shock to a person whose heart has stopped beating normally, and this is shown in figure 15a. And two paddles are initially placed in contact with the patient's chest, and a simplified defibrillator circuit is shown in figure 15b. And when the switch is at position A, the capacitor is charged until there's a large potential difference across the capacitor, and there's a 32 microfarad capacitor in the diagram. So the capacitor can be considered to be fully charged after 5 time constants, and the time taken for the capacitor to be considered to be fully charged is 10 seconds, and we've to determine the resistance of resistor R. Well, if 5 time constants is 10 seconds, then tau, the time constant, will be 10 divided by 5, which is 2 seconds. And now we know the time constant, then the relationship we're looking for is tau equals RC, and we've to determine the resistance R. So R will be equal to tau over the size of the capacitor, so that's 2 divided by, and it's a 32 microfarad capacitor. There it's there, in the middle of the diagram, 32 microfarads, so let's pop that in as 32 times 10 to the minus 6. And that gives you an answer for the resistance of 6.3 times 10 to the 4 ohms. In part B, during a test, an 80 ohm resistor is used in place of a patient, and so the switch is moved to position B and the capacitor discharges through the 80 ohm resistor, and the initial discharging current is 60 amps. Now, the current in the resistor will fall to half its initial value after 0.7 time constants. And we have to show that the current falls to 30 amps in 1.8 milliseconds. So if the capacitor is discharging through a different resistor, an 80 ohm resistor, we're going to have a new time constant. And that time constant will be the resistance of 80 ohms times the capacitor's capacitance of 32 times 10 to the minus 6. And that gives us our new time constant of 2.56 times 10 to the minus 3 seconds. Now the current will fall to half its original value in 0.7 time constants. So we just want 0.7 times that new time constant. So 0.7 times 2.56 times 10 to the minus 3 gives us 1.8 times 10 to the minus 3 seconds. And that's what we were asked to show, but let's write it as we were asked. It's 1.8 milliseconds. Remember, it's a show question, so show your answer exactly as it's given in the question. So the current falls to half its original value in 1.8 milliseconds. Let's have a look at the marking instructions for these first two bits. So, pretty straightforward, the same relationship used twice, but firstly to find the time constant in the charging circuit, and then secondly, the time taken for the current to fall to half its original value in the discharging circuit. Quite tricky there because they're two different resistors. Anyway, moving on, 15 part C. In practice, a greater current than 30 amps is required for a minimum of 5 milliseconds to force the heart of a patient to beat normally. So an inductor of negligible resistance is included in the circuit to increase the discharge time of the capacitor to a minimum of 5 milliseconds, and this is shown in figure 15c. Now the inductor has an inductance of 50.3 millihenries. The capacitor is again fully charged, then the switch is moved over to position B, and we have to calculate the rate of change of current at the instant the switch is moved to position B. Well, we need our relationship here that's got rate of change of current in it, so it's the back EMF equals minus L times di by dt. And remember, your back EMF is equal to and opposite to the supply voltage when the switch is closed. So if we move that switch to position B, then the voltage across the capacitor when it's fully charged will be 4.8 kilovolts. So the back EMF that's produced will be negative 4.8 kilovolts. So negative 4.8 times 10 to the 3 will be equal to the inductor's value, which was 50.3 times 10 to the minus 3 henries, times the rate of change of current. And if we rearrange that to find di by dt, then the rate of change of current, di by dt, will be equal to 4.8 times 10 to the 3 divided by 50.3 times 10 to the minus 3. Remember, those minus signs will cancel out, and we get a final answer of 9.54 times 10 to the 4 amps per second. There's the marking instructions. Standard 3 marker, but don't forget to include your negative sign in your back EMF. Okay, 15C part 2. It would be possible to increase the discharge time of the capacitor with an additional resistor connected in the circuit in place of the inductor. However, the use of an additional resistor would mean that maximum energy was not delivered to the patient. Explain why it's more effective to use an inductor rather than an additional resistor to ensure that maximum energy is delivered to the patient. Well, when there's current in a resistor, heat energy is always produced. So therefore we're going to lose some of the energy to the surroundings. But when you put an inductor in the circuit, then energy will be stored in the magnetic field around the inductor, and that energy will be released and then passed on to the patient as the magnetic field around the inductor collapses. That's pretty tricky. Here's the final marking instructions then. See part 2, additional resistor will dissipate energy, but the inductor will store energy and then deliver it to the patient as the field collapses. That's it then for capacitors and inductors, which means we're nearly done, but I'm going to do one more video, and I'm going to do it on graph work and experimental methods. And we'll cover a little bit of uncertainties in that as well, so we'll definitely do 2020 question 16 and another one as well. Anyway, we'll see you in the next one.